So I have this group of 3 questions. This and the next 2 questions. They all involve polarization of light, and they will all use something called Malus's law, which I guess you could technically look it up from the textbook and, I don't know, use it or memorize it as a formula that's given in the textbook. But let me maybe give a brief explanation of why I don't actually memorize Malus's law as a separate law. I mean, you could memorize it, say that the intensity transmitted is equal to incident intensity times cosine of theta squared. Do I have it memorized? Sometimes I can't tell the difference between me having it memorized and redriving it in my head as I'm talking. So this is how I would derive Malus's law from scratch. It's based on the understanding of electromagnetic wave as a wave of oscillating electric field. So this is how we usually represent polarization. So imagine you have a beam of light, like originating from some spot, going to some other spot. I'm drawing a perspective view. Then you can kind of represent this, and I'm gonna omit the magnetic field component of it, understanding that it's there, it's perpendicular to electric field, and E cross B gives you the direction of propagation. Understanding all that, I'm just gonna draw the electric field. So in an electromagnetic wave, the electric field might look like this. This is the kind of snapshot in time of this electromagnetic wave. This is the E field, and it's oscillating as this wave goes. And this is how we represent the polarization of light. Imagine taking a point here, kind of sampling a particular point along the propagation of light. And at this point, we might look at the direction of the electric field. And let's say the electric field that's along this axis was oriented as, so let's say this is my reference, theta equals 0. And let's say my electric field is oriented along this axis here. So depending on which point along this axis you choose, electric field might be this full length here, or something smaller, and then reverse the direction, and then something going in this direction, and then full length. So to represent all those possible orientations and lengths of electric field, we draw this as an indication of the direction of the linear polarization. And it has some angle theta. And this is a kind of visual representation of electric field. And let's imagine this light then goes through what we call polarizing filter. We have a polarizing filter. Let me draw it further down so that they don't overlap so badly. Let's say there's a polarizing filter with some kind of optical axis. And let's say the optical axis is in this direction. And as this light comes through, it's still oriented this way, the way it was before. There's no reason for it to have changed. So what this polarizing filter does is it takes a projection of this light along its axis. So you can imagine this as a vector that can be broken down into the parallel component and the perpendicular component. And what the polarizing filter does is it only lets in this component of light. So if you had incident electric field of light, then you have transmitted electric field of light. And looking at this geometry, you can figure out what is the amplitude of this relative to that. Based on this angle, let me call that phi. We can say the transmitted electric field of the optical electric field, the magnitude, is the incident electric field times this projection here. It's the adjacent side, so it should be cosine of phi. So that's that's the role that polarizing filter plays in an optical setup. It takes the component of optical electric field parallel to the optical axis of polarizing filter. And the final key that will give you Malus's law from this geometric fact is this relationship that intensity of light wave is proportional to electric field squared. This language, proportional to, is doing a lot of work here because there's a lot of like numerical factors. So to do it properly, I have to work out what's called a pointing vector that you might have seen in a previous physics class. Pointing vector does give you, I think, intensity of light. But for our purpose of optics, we can kind of sweep all those details under the rug, and we can just rely on the fact that intensity is proportional to the electric field squared. So when you have this relationship between transmitted and incident electric field, then all you have to do is square this entire thing to get the relationship for the intensity. And that's where you get cosine, the angle between them, also the way I'm using it, phi squared. So that's Malus's law. And this kind of underlying understanding is what I use to say well, you don't need to be taught this separately. If you understand the nature of light and its polarization, then this is the kind of law that anyone with some knowledge of trigonometry could work out for themselves without being told that this is a law. So with that, let's finish these three easy questions. The first question asks, what angle is needed between the direction of polarized light and the axis of a polarizing filter to cut its intensity in half? Oh, so if you know some trigonometric facts, this is easy. 45 degrees. And this is what this is the thought process in my head. I'm looking for this factor of cosine angle squared to be 1/2, or the cosine of the angle to be 1 over square root of 2. That sounds like a cosine of a special angle, 45 degree. That's my thought process. And if you can do that, then great. Do it. I mean, no reason to drag it on. Like, this is an easy question. You don't have to make it hard. Let's move on to the next question. There might be some questions where you can't quite do, oh, is this going to be I don't want to do the same thing over and over. Let's do a new version. Okay. Yeah, 40% is awful enough there. So you do actually have to now do the math. So now actually doing the math, what it would be is you say, okay, the angle, so you have this relationship, the transmitted intensity is equal to the incident intensity times cosine phi squared, and putting in that information about the 40%, what we are saying is that cosine phi squared is 0.4, or yeah, intensity to 40%, not by 40%. So cosine of phi is equal to square root of 0.4. Oh, I don't think I can do that in my head. So phi, assuming it's an acute angle, should be arc cosine of square root of 0.4. So let's just use Wolfram alpha for that. So arc cosine of square root of 0.4. The question is looking for answer in degrees, so I'm gonna look for the answer where it's been converted to degrees. 50.77. Good. All right, one last question remaining, and I think it's also similarly easy one. I probably spent more time explaining Malus's law than was necessary to simply use it to answer the question. Not this one, this one. All right, so this is third and the last question. It says the angle between axis of two polarizing filters is that. Oh, this time we are given the angle, and then, yeah. So we just plug in the formula. Cosine of 37.7 degrees squared. Oh, 0.626. And because this time I don't have to do the conversion from radian to degree, this should be exactly by what exactly the 62 point or 0.62. It didn't ask what percentage. If it had asked for percentage, I would multiply this by 100, but here it's just multiplicative factor. So that's a third and the last question. I really want you to complete all these sets. So that's why I'm doing it. Again, once you know Malus's law, these are easy questions. But now I've done it, I never have to worry about it again.